Hello and welcome to lecture 18, back to physical design. So we did an interlude of open source hardware project management, and now we're going to do um, one more physical design lecture. So, as title tells you, optimizing for delay. And so what we mean by that is what can I do to my design to improve delay, which is usually correlates with performance, right? So, um, to cover that, we're going to cover a few things. We're going to cover a little bit of physical details, understand why there's delay in hardware and what are kind of sources of that, and then talk about ways to reduce it. So we actually, once again, are back to our sweet day of having a little bit of code to show. So let's have a little bit of code set up for later on. Um, in a combinational circuit, there are two types of delay. There's gate delay, which is, delay that goes through the logic gates, which of course are transistors. And then there's the wire delay, the delay it takes for that same little travel between gates. And both of these delays are significant. Depending on implementation technology, they can vary, right? In an ASIC, the gate delay may be your primary delay, and the wire delay, assuming your placement and routing is good, may not be as painful. Versus an FPGA is completely the opposite. An FPGA, the wire delay may be easily 70 to 80% of your delay. Um, and so it's important to keep that under control. So let's talk about what kind of causes delays for both of them, right? So gate delay, of course, these are physical things. It takes time for physical things to actually switch, sure. But other things that make it worse, right? For example, the bigger the gate is, in other words, the more inputs it has, the more complicated the function it performs, that can cause more delays. So the term for number of inputs is fan-in. So a higher fan-in gate can increase delay. So for example, you as a coder may have a reason why you want a 10 input AND. Rest assured, the CAD tools will know what to do with that, but they will not build a 10 input AND gate in one hop, right? They will break it up into multiple 2 or 3 input AND gates because they're going to be faster combined together than one 10 input AND gate. Um, Meanwhile, for the wire delay, it takes time for signal to propagate. It has to go a long way. That causes problems. FPGAs has to go a long way, and the means it's going through it themselves are kind of slow. What else make wire delay worse? Fan out, meaning that rather than just going to one location, it goes to multiple locations. That basically increases the load that is in the number of places need to receive that signal, and thus it requires more current to satisfy all them, and thus it takes more time to fill it up. And once again, fan out is also really painful FPGAs. So FPGAs, if you spend time optimizing for them, you'll find that, yeah, you kind of want to have limited fan in, limited fan out, limited wire delay. You really got to get it very optimized design to really minimize your delay versus on ASIC. Sometimes you really can just kind of do a decent job, and modern transistors are very, very fast. And, if as long as your design is not poorly made, you can get a decent delay if you don't have a very aggressive clock period. Okay, so how do we measure delay? Well, we can measure it in time, right? So things like nanoseconds or picoseconds. Usually, picoseconds is more common, right? Because you have a gigahertz frequency. That means you have a 1 nanosecond period. So thus, the things you make up that one clock period are going to be less than nanoseconds. So nanoseconds are kind of a historical term, but really, you're talking picoseconds normally, right? Um, on ASIC, FPGA, of course, you are talking nanoseconds. But it's actually a really interesting term, which I've spent a minute covering people in case they haven't seen it before, something called FO4 or fan out of 4. This is an interesting unit for delay. So you can think of delay as it takes, some number of picoseconds, let's say 200 picoseconds to get from point A to point B. Or you can think of that in terms of fan out of 4. And the reason why this is helpful is as technology keeps getting better and better, we keep getting smaller and smaller transistors, they're also getting faster and faster. So at faster and faster transistors, what is 1 year a reasonable clock period is not good in next year, right? There was a time period where in span of about 10 or 20 years, clock periods went from tens of megahertz to gigahertz. And it was just kind of boom, it was a really big exponential leap. Nowadays, clock periods are improving much more slowly, so perhaps people don't appreciate the importance of this. But those time period clock periods improve dramatically. And so the way to kind of capture how much intrinsic delay there is, there's this FO4. So FO4 is designed to be somewhat technology agnostic, right? So what you do is you find for your implementation technology, what is the delay for one inverter to drive 4 inverters, right? So since there's 4 inverters, that's a fan out of 4. Whatever that delay is for technology, you then divide the latency you have to get the number of fan out of 4s that would take, right? So in order to get the equivalent delay in the technology would be, certain number of levels. So, for example, you see on the slide, back with the Pentium 4, which of course, is more than 20 years ago, uh, the fan-out 4 latency was 18 picoseconds, which is pretty fast, right? That's pretty quick. And so that entire processor, its critical path was a 16.3 FO4 delay, um, which I know may not mean a lot to folks, but if you're a computer architect, if your FO4, if your processor is below 20, that's a highly, highly optimized design. Someone may be able to look up what is the fastest ever FO4 for a computer processor, which may not necessarily be the fastest ever frequency, but in terms of logic depth, the shortest. Uh, I would be surprised if anyone got too far below 14. Like 12 maybe is possible, but like 8 or 9, no. At that point, it's rough. Um, and so yeah, so at 16 FO4, that's a really, really, really short uh, critical path. Understand today's processors we're using on our iPhones, whatever, are probably in the 25-ish range or 30-ish range for FO4s. You just write random logic, you probably be in 40 or 50 FO4 range, not meaning to. And so yeah, so 16.3 FO4 is really fast. So you talk about delays. Sometimes we'll talk in terms of FO4 as a way to kind of make it more technology agnostic. Yes. I forgot, but I believe Wikipedia links to the source links to Wikipedia. So let's see if how my link is. ITRS from 2003, FO4. Okay, now we're gonna play with fire and look at what Pentium 4 on here. 90. I saw here read 90 nanometers from the audience. Yeah, so 90 nanometers. Oh my gosh, yeah. So for those counting at home, right? So go from 90 to 65, that's one shrink. 65 to 45, that's two shrinks. 45 to 22, three shrinks. 22 to 14, four shrinks. 14 is kind of the place where Intel's technology fell off the rails. So 14 to 10, sure, we can do one more shrink. 14 to 10, that's five. Then at 10, Intel's changed your naming. And so heaven knows. But we're talking at least five shrinks. In other words, we're not talking in speed terms, in terms of transistor terms, you're talking at least 2 to the 5 value, 32 times more transistors. The reality is actually modern chips are also bigger. So it's even more than 32 times more transistors. Um, so yeah, interesting detail. Cool. Okay, so that critical path I alluded to. What is critical path? Get everybody on the same page. That is the longest delay path through your circuit. So under worst case conditions, this takes the longest to toggle. And this is important because your clock needs to be longer than the critical path delay. If your clock period is shorter than your critical path delay, that means there's a scenario in which a bit can change and it won't be captured and you'll get the wrong answer. So whatever this delay is, it is kind of the key limiter. And so people often may say, oh yeah, I'm trying to shorten a critical path. It may be physically shorter, but more importantly, it needs to be less delay, right? And so what's interesting with the critical path is that whatever your critical path delay is, that's going to limit your design. Every path that is shorter, less delayed in a critical path, you actually kind of almost don't care about, right? You're like, you know what? That's not my critical path. I don't care about it. Smart CAD tools do things. You know what? This is not the critical path. I can use slower logic gates here to save power, and it won't hurt me, for example. So it's a common optimization. Um, so if you have an opportunity to reduce a critical path delay, you have to help you in two ways. Number one, of course, shorten critical path. You can reduce your clock period, which in turn lets you crank up your clock frequency and go faster. Or this is an interesting one. If you reduce your critical path delay, keep the same clock frequency, you can turn down the voltage to your chip. So as you decrease the voltage, your circuit's going to run slower, but it's going to take less power and you're going to save energy. So when you reduce that voltage and you save power that way, um, as a result, you're going to save power, right? So for the same performance, you're going to now take less energy. That's a win. So either way, if you're reducing critical path is really desirable when you can do it. And so the question is, how do we go about doing all that stuff? Well, tools perform something called static timing analysis, STA, to try to figure out where that path is. So this is a oversimplified example showing, what STA looked like 40 years ago. Um, of course, modern STA tools are much more clever and have much more detailed models, but you can think of it as, assigning a delay to each component and then starting, okay, they all arrive at a certain point, and each step of the way kind of tracking as signals arrive, and then considering the worst case one, right? For example, at this NAND gate, we have one input arriving at 10 units of time, one arriving at 3 units of time. And so we're worried about the worst case. So we're going to think about 10. This gate takes 2. So, of course, the output's going to change at latest 12 time units later. And, of course, going across this wire, we're going to say it takes 2 units of time. So then it arrives over here at 14 units. And once again, this changes earlier than this one. In the worst case, we care about this one. So you can imagine kind of doing this in a two-pass algorithm where basically you propagate the delays from the inputs to the outputs, and then you trace backwards to find that path. So for example, if we could have that, I'm not shown, I'll draw it out with my mouse. Okay, starting from the output, finding the last arriving signal. Okay, so this input's the problem to that input to then either one of here. So the critical path is through here like this, right? Now it's actually the prior slide, I guess, right? Cool. So stack time analysis can be used for a number of things. Oftentimes use it for worst case. That's what you're trying to find. What's this critical path delay? And you can run at different times. You can run it early on in your design process, and so just after synthesis. So in other words, it's taking your design, turning it to logic gates, but it doesn't really have accurate models for wire delays. Or we can run STA after you've done your post placing and routing, so you really can make sure it's going to be more accurate, right? And so these STA models can get a lot more precise, right? They can have distributions for these various latencies. They can consider process variation, temperature, voltage, etc. Um, cool. So let's say your SK tool has told you you have a critical path and you need to go in and fix it. This is actually where a lot of time can be sunk if you're a designer if you're not careful. So getting your design function correct, takes time obviously, but optimizing critical path can sink a lot of person hours if you're not careful. And so what happens? Well, basically what happens is you have a target period, and if you're there, you're done. If you can't reach the target period, you have some number of paths that take too long. So, for example, if you look at the delay across all the paths in your design, most paths are really short and the delay is good. This is kind of histogram, and you're fine. But a handful of paths are longer than your target period. Shoot, you got to go one by one for these paths and then figure out a way to break them up and make them shorter. So, as you start fixing all these, eventually you're going to keep making these paths reach the target period, in which case, after a lot of optimization, your distribution might look like this. We have a lot of paths just barely meeting the timing target. And at this point, you've reached your timing target. That's great. If your boss comes over and tells you now, I want to go 5% faster, you should give that person a understandably angry response because you already optimized for a certain target. And now you actually have a lot of paths at that target latency. And so thus moving them all down 5% is going to be painful. Um, and so, yeah, so it's really worth optimizing the critical paths. Sometimes architecturally, when you reduce these critical paths, you introduce pipeline hazards. We talked about that in architecture classes, in which case the periods improve, but maybe not the throughput if you're not careful. But typically what you do is, yeah, you find the longest delay path, the critical path, look at its delay, figure out ways to break it up, and then keep going until you get all of your paths below that period. Now, the tools do this on their own. So to some extent, before you even look at it, the tools already tried to recognize, oh, wait, you told me a target period of this. This path is longer than critical path delay. I'm going to see what I can do as a tool. The tool can do things like using faster logic gates. It can do things like resynthesizing the logic to try and make it shallower. It can use higher power gates that are faster. It can try to place them closer to reduce the wire delays. It can do a variety of things. But at some point, the tools may tell you, you know what? For design you've given me, I can't do better. You got to fix it yourself. I said, it's going to be very time consuming, but sometimes you have a need. Cool. So, like I said, how can you fix the delay? The tools can do a lot. And you want the tools to do a lot. Remember, one of the themes of this course is make tools do the work, right? And there's decades of work in EDA to try and improve this. They can do a lot. But the key thing the tools can't do is change the semantics of the design. So if you have specified in your RTL a certain behavior, they can't change that behavior, right? So some people in this class have been asking me all quarter about what about HLS, high-level synthesis, right? High-level synthesis, as the name implies, you are specifying the behavior of your design at a higher abstraction level. Thus, in some ways, it gives the tools more leeway to optimize because they aren't breaking the semantics, right? In HLS, for example, you might say functionally, oh yes, this component does this operation. In RTL, you specify not just the operation, but the exact cycle level timing of the operation, right? And so thus the tools or have their hands tied on what they actually can do in that case, right? So the tools are doing everything they can, but at some point, there's new things they can't do because that would change the RTL semantics. And so what can a designer do? Well, guess what? You can recognize those spots where you're being held back by the design semantics and actually change design such that it's now able to fix this thing, right? Of course, major architectural changes, the tools right now don't do those. Maybe in a few years, LLM assistants will do that for us. Who knows? But for now, major architectural changes come from humans. And then finally, really the kind of goal is to make tools do the work. So recognizing what do I need to do to enable these tools to do more. So sometimes you got to change design to make the semantics kind of let it do more. Sometimes you got to read the tool documentation to kind of turn on more flags. Sometimes you got to annotate parts of your code to really suggest to do certain optimizations in certain places. Whatever it takes. But I recommend this is really kind of a work with the tools, use the tools situation rather than a distrust the tools and try to do it all manually because guess what? You can't, right? If you're going to design an 80 billion transistor chip with a big team, even if you have a big team, you need to use a lot of tools. Questions? Okay, so then the most classic way to reduce delay, of course, is pipelining, right? So given a long combinational path between two registers, right, the critical path is basically the maximum time path between the register's output and the register's input. So let's say you've run static timing analysis, STA, and you found this is the critical path, and it's a long path, and the tools to try to optimize it, you can't. So what do you want to do? Well, maybe you want to put a register in the middle of that path. Thus, the path is shorter. Great. Easier said than done sometimes, right? What does it require? Well, notice how this original design, there is one unit of data in this critical path. Now that I've pipelined it, I need to have data here and data here. So in other words, you need parallelism. Fortunately, most hardware problems do have parallelism. Basically, I would argue a lot of applications have parallelism, and one of the applications that has any hint of friction of parallelism is actually trying to build a general purpose CPU. So if you take architecture classes, probably spent a lot of time studying pipelines and pipelines hazards. The nature of our ISAs is very sequential in some ways, and so thus we have this limited parallelism. But for most real applications, you tend to have abundant parallelism. So usually pipelining is very much an available technique. You have a lot of data, and thus you can pipeline. And so yeah, when you're pipelining, of course, you want to balance the delay, right? If you have, this long delay path here and you put 80% here and 20% here, that's not going to be good. You'd rather be closer to 50-50, so that way the critical path isn't that long. And so when it comes to placing these registers, as a human designer, usually you kind of can place them in places that make semantic sense. We've kind of seen in this course, for example, maybe you have the coupled interfaces between modules, and at the boundaries of those coupled interfaces, you have registers, right? That makes sense. That's easy to kind of understand semantically. Um, However, when it comes time, that may not correspond to what's the best place for the logic delay, right? And manually moving registers through your design before and after certain combinational elements, that can be very labor intensive. So what can we do about that? What's the course theme? The other one, make tools do the work, right? So make tools do the work is this next one. So yeah, if figuring out where registers need to go for balancing latency is tricky, make tools do the work, right? Um, this technique called retiming or register retiming, which will move registers forward and backwards through the combinational logic to try to balance these paths. So this is not a trivial transformation, but a lot of CAD tools support it. If you've heard me talk about research, I complain about how finicky the retimer is in the Xilinx Vivado tool chain. It's really not as robust as you would like, but if you use any competitive commercial ASIC CAD flow tool, oh my gosh, they are so good at retiming, and they've been good at retiming for decades. Um, so as long as there's enough registers, they actually can move these registers backwards and forwards through the logic, right? Um, Now, sometimes there's situations where topologically, if it moves the register, it's going to cause certain challenges. For example, maybe you have, let's say, like a 4-bit bus here. If we move back too far in this path, what was a 4 register now needs to become an 8 or a 12-bit register. The tools can figure it out, they'll do it. Other times, you topological constraints where it really can't move registers. Maybe there's some sort of tight feedback path, and moving it there is going to break it up. It's going to be best as it can, but obviously sometimes there's constraints, right? Some tool flows are specific. We only move registers forward or backward, but not both ways. And so as a designer, you kind of need to put these extra registers on the other side of the ass. So you put extra registers to the front or the back, and that's going to move them the other way. Another interesting challenge with retiming is just a minute ago I told you one of the challenges for CAD tools is when you change the observable semantics of your design, that's going to make it, you're breaking the contract. Guess what? You move registers around, you are breaking the contract, right? Someone wrote RTL. RTL, of course, stands for Register Transfer Language, saying this register on this cycle has this value. You move registers around the logic, the meaning of the register is going to change. So you actually are breaking the semantics. So RTL, register retiming actually is a RTL semantics breaking transformation, but we tolerate it because it's so damn helpful. But also, but now let's come to verification, right? Now for verification, maybe verification is based on the values of the registers. Now the registers have different values because you've moved them around in design. So what do? That's something that's been kind of cutting edge for the last 10 plus years is, okay, you do register retiming. Now the register semantics have been changed. If you change where it is in the design, you can use things called logical equivalence checking or LEC to figure out how to transform the values in the registers when you're verifying to make sure it matches what it should have been. So in other words, you move registers around, you change what these registers represent, but there is a logical transformation to get from what you have to what it should be, and you can still kind of do verification with it. So um, retiming is really, really important. And so as a designer, our goal is to kind of enable retiming to happen. And guess what? It's as easy as just placing extra registers, making sure your catch tool supports retiming tools, move them forward or backwards depending on what the tools require. Questions, comments? Yes. Yeah. Yeah. The question about the verification and the LEC, the logical equivalence check, is that automated? It can be. So a logical equivalence check or a LEC is a key part of a lot of verification flows. Because basically what you want to do is you're going to somehow transform a design in some way, and you want to convince yourself that it's still the same design. And so, yeah, with a LEC, you put in design A, modify, now you get design A prime, and you compare the two, and you convince yourself they're still equivalent. Oh, for sure. Yes. The question is, would retiming perhaps make this a little tricky for designers to understand what's going on? Definitely. So the good news is, as a designer, right? If you're going for functional correctness, you can do that before retiming is applied, right? You can just get design functionally correct. Retiming is part of the physical design process where you are trying to minimize the critical path with the help of tools. And hopefully at that point, you are not chasing functional bugs. Guess what? In the real world, even though you're not supposed to be chasing functional bugs, they may occur, right? The tools may have a bug, you have a bug that slips through. And then what do? Then you got to lean heavily on your leg tools to try to figure out how you're going to verify and debug this. But yeah, if you can, you'd rather debug on the unretimed circuit, get that function correct, and then the retime is a way to get high performance when you actually make it physical. Cool. So let's say I want to do retiming in Fizzle. What do I do? Like I said, it's as simple as putting the registers on and having a CAD tool supports it. And the commercial ASIC tools are fantastic at retiming. Some of the open source CAD tools are okay, getting better at it. And really, I'm going to give my mark of shame to Xilinx Vivado for being poor at retiming. Um, so in the best case, what are you supposed to do? You really just got to put on extra registers and then let it move them around through design. And in the spirit of a generator, this is easy to parameterize, right? So you can imagine, as I've seen this example, as some sort of pipeline module. I have the pipeline depth as a parameter. I write the functionality for the module combinationally, however I need to be done. So that's very easy for me as a designer, right? Just write functionally using, take this thing, do a setup operation to it, do a mux, do an add, whatever you need to do, shift, multiply, it's expensive. I can do all that stuff. It's very easy to write like that, right? You're not worrying registers, right? Just writing the logic as you'd like to write the logic. And then at the end, you put this pipe in there. Pipe is going to give you that delay register we had earlier in the quarter. So remember earlier in the quarter, we showed like, oh, we want to do n registers in sequence. We can call that a shift register or delay line. It's actually in Chisel standard library as a pipe. So it's just going to be pipeline depth and registers one feeding into next. It's not a FIFO. Remember the FIFO before was very smart about, has a couple of interfaces. Maybe you have that flow parameter to kind of bypass. You may have the pipe. No, no, no. The pipe is really simple. The pipe is just n registers in sequence. It always goes through. There's no stalling. There's none of that stuff there. It's just registers in sequence. But as a designer, it's easy, right? You just write the conventional logic. You can even test the conventional logic. And then later on, you can check on this pipe here. Now you have pipeline depth registers following your design. And then the CAD tools can go in and do the retiming. Um, Now this is for a design where tool that does backwards retiming. Maybe you're working on a tool that does forward retiming, in which case you put the extra registers at the front of the design on the inputs, it's rather than the outputs. But you can do that. Cool. Questions? Okay. So step one is usually to kind of avoid these horrible critical paths. Usually pipelining solution. Um, Retiming works great from the CAD tools, making tools that work, but that requires registers to be there. So the human designer, a lot of what you need to do is kind of trying to figure out where might you need more pipelining and actually put registers in, or at least close, so that we can be retimed to where we need to be. The other way you can improve delay is to recognize you actually just have convolutional logic depth that's unnecessary, right? Sometimes there's a lot logic depth. You can finesse the logic to actually make it more balanced, right? And so, like I said, the tools are really good doing this on their own. And then when they can't do this, it's because you have inadvertently usually specified things in a way that constrains them from doing what they need to do. And so, what are some examples of things you might be doing that might not be very good? For example, all quarter, I've shown you examples using things like recursion, for loops, even fold left, or we build these generators linearly, right? And guess what? Linear works until it doesn't work, right? At some point, maybe that delay is going to be too big. We should do a tree. We'll show that in a minute. Sometimes you can put pipelining in there. Um, as always, when optimizing, before going off and doing all these things, you need to make sure this is the critical path, right? You may have code that does a linear construction of something, but guess what? If it's not the critical path, don't worry about it, right? It's only if it's on the critical path that you will fix it. Other times, something might look bad to you, and you think, oh yeah, this has got to be it. This has got to be it. But guess what? It may not be the critical path, right? And the tools may figure it out. I shared an anecdote before of how, in Chisel, if you use a VEC in the Verilog, at least the old version Chisel, the new version with Chisel 7 and FurTool does better with system Verilog output. But the older ones, you're going to see like a 500 element VEC is going to lead to 500 muxes, right? Literally checking, is this element 0? Is this element 1? Is this element 2? Is this element 3? If it is, it gives you the element, otherwise it passes down this mux. That sounds really bad. That looks really bad. Every catch I've seen in my career so far has fully understood what that meant and did the right thing. It turned that, 500 2-to-1 muxes into the appropriate deeper muxes in some sort of tree. And so the catch list figured it out. And so maybe you're handling it just fine. So really make sure before you dive into optimizing stuff too heavily to make sure it's needed. Um, cool. So the thing we're just talking about, let's say you're trying to add up n numbers. Using some of the reductions technique directions we talked about earlier, you might, just keep calling reduce n minus one times. So guess what? You have n minus one adds in a linear sequence. That's a really deep depth. That's the delay of one adder times n minus one times, right? It's a lot of logic depth. You put them into a tree where you're kind of, fanning in better. Um, Instead of being linear depth, it's logarithmic depth, right? So that's going to be good. It's the same number of adders. It's just going to be rearranged to be more efficient in terms of delay. Cool. Um, how might I code that? Let's see an example. So let's say we're doing something called pop count. So pop count is counting the number of ones in a multi-bit signal. So in this case, rather than having a uint or a vec, for simplicity, I'm using a seek of bool. So remember, seek is a Scala collection. Bool is a chisel one-bit type. So I want to, given this, I want to return a uint, which is how many of those bits are currently one. So this is definitely hardware that, is going to change based on the value of the input it's given. So how might I do this? Well, if you're doing this recursively, here's one way of doing it. I could say, hey, if you give me an empty collection, well, there's 0 ones there because there's no elements. It could be 1. Otherwise, take the first element, which is going to be a single bit quantity, 0 or 1, and then add that onto the remainder of this collection. So that's what the dot tail is. So when you have a seek in Scala, dot head is 1 element and dot tail is n minus 1 elements, right? So, okay, so you can see how recursion goes through one by one and put together n minus 1 adders, right? So if I go back a slide, you basically do something like this, right? Um, okay, how does that work? So let's say I actually take this function, chuck it into my module, and actually run it, and then print the Verilog. Yeah, you can see it. It's not pretty, but basically, it is doing the adds each level. A lot of the clutter you're seeing here is concatenating on zeros as it kind of does this growing addition. Um, but it doesn't. Okay, what if we try to do it tree style? And you can see here, I'm kind of giving away the fact this is copied from the Chisel Standard Library. Well, in the tree style, what you're going to do is, okay, given zero elements, obviously it's going to be zero. Given one element, sure, I have to, return that one element. But now if I have more than one element, I can just break it in half, right? Left half, right half, and recurse, right? So it's divide and conquer. And yeah, this is using that Scala syntax. So we'll take n minus two elements, the first n minus two elements, and drop the second half of them. And meanwhile, drops the first n minus two and keeps the second. So with take plus drop, you get all the elements covered. You kind of split it in half. And yes, I like the ability in Scala to have the space and no parens, but this is equivalent to doing this, of course, which is in the more modern era recommended style. But I thought their stuff was kind of very elegant. Um, and let's actually turn that on in the code. And yeah, you can see now we just add the bits up. So this looks a lot more intuitive. The output is not as gnarly. Um, the other one, the tools may be able to optimize on their own, but this is also helpful. And then, of course, you may wonder, well, gee, what does the standard library do? Well, I already told you it's tree based and you're going to get the same code. Cool. Questions? So that caps that. So let's talk about what we talked about this week, right? We talked about getting ourselves aware of what it means to optimize the physical design, what that talks about. Architecture level, I kind of focused a lot on the first lecture on memory, because memory is a really expensive, very important item. We then went on a detour talking about open source project management and what it means to run a project. And then today we talked about delay. Before we close, I want to remind folks that on Monday, your project proposals are due. And they'll be using the lectures time slots next week on Tuesday and Thursday to have project group meetings. So basically, the way it works is I get the proposals on Monday. My job Monday night is to read through them and prepare feedback for Tuesday and Thursday. I'm also going to send out, once I have the project sent to me, the schedule for which groups are on which day. So that way you know which day you come in. So you need to come in on the day that your project proposal is discussed. You are invited to come to both days. And I recommend sticking around for other groups, especially on the same day as you, because you can learn a lot by hearing this conversation. I'll be suggesting certain things. You may say, oh, wait, I may have a similar concern. You can kind of hear that feedback and kind of gain from that feedback. Um, for the handful of undergrads who are taking the conflicted course with the capstone, make sure to either message me or mention that in proposal. That way I can schedule on the correct day to avoid conflicts. Any questions? Yeah. Oh, good question. So what about other assignments? So yeah, we are shifting gears, folks. So we have homework 5 due tomorrow. There will be both a homework 6 and a lab 6. However, they are not going to be what you think they are. So we're kind of moving in the project direction. So the project proposal is your next thing after homework 5, and that's due on Monday. After that, there will be a homework 6. It's not a massive coding assignment. It's actually the code review assignment we're talking about. You're going to kind of get experience doing a code review. Um, really starting after homework 5, the majority of your work for this class will be all project related. In a few weeks, we are going to have a lab 6, which is based on Chisel formal verification. At that point, you're already in the middle of your project, but it'll be kind of a fun aside. We're doing it later this term because that's when we had the good fortune to have a good guest speaker coming in and talk about the Chisel formal, the person who created it. So we have a few guest lectures coming up. They're all going to be great. We have other languages being discussed. We have Chisel formal. I'll be advertising more about that in those lectures. We hope people to come and ask exciting questions that are happening live. Cool. Other questions? That sounds good. Okay.